Today, we're going to discover exotic creatures that might spit out bricks to breathe. But first, remember there's something big we all share. You, me, my grandmother, and my dog. Lichens living thinly on rocks, plus a jellyfish and bamboo stalk. A mushroom, a log, a fish, or any cactus. All of which are built around one single thing, carbon. On a molecular level, this element forms the framework of living things and is central to all processes involving living matter. Blinking, biting an apple, digesting, breathing. Every step involved in even the smallest event concerning your body calls upon these atoms at some point. It's not for lack of trying, but we've never found anything in living nature that isn't built around long carbon chains. But can we even imagine the possibility of life built on anything else? A life whose cornerstone, deep within its flesh, at the very heart of its matter, would be of a different nature. And that's where it gets unsettling, because we know of an element that life, for the most part, doesn't care about, and which has a lot in common with carbon, while being much more abundant than it on Earth, namely silicon, the atomic element on which almost all modern computing relies. But before we go find out why it might be exciting to imagine creatures built around it, we'll need to take a closer look at the reasons behind the astounding success of C. Why did life on Earth build itself around this element and not another one? When you think about it, there are many atoms in nature. Carbon is the fourth most abundant element in the universe by mass, but only 15th in Earth's crust. Already, carbon has a kind of superpower, namely the ability to form up to 4 stable bonds with many other elements. But most importantly, with itself creating long chains, it can give rise to large molecules, such as caffeine or theobromine, which help give chocolate its very distinctive bitterness. And yet it differs from caffeine by only 1 carbon atom and hydrogen. And even then, these molecules are relatively simple if you compare them to a vitamin. Here, B12 rich with more than 70 carbon atoms, which is itself tiny in size compared to the truly gigantic macromolecules with insane complexity that long carbon chains are capable of forming. And some of these, such as proteins or DNA, can contain millions or even billions of atomic elements. The thing is, to be able to build such large molecules, you have to be flexible enough to allow transformations and modifications by reacting with your environment, while also being stable and robust enough not to fall apart at the slightest disturbance, and thus make things last over time. And it's this relative flexibility of the bonds, this slight weakness, that gives carbon its greatest strength. By allowing it to be versatile and to cause, according to the play of chance collisions, the appearance of a truly staggering number of new molecular forms. Consider that, to this day, more than 10 million different carbon compounds are known in nature, and this number is probably only a small fraction of those that actually exist. In fact, it's partly because the number of combinations that can be made from carbon is so staggering. That's why the study of molecules based on this element is called organic chemistry, while all others are grouped as inorganic chemistry. And so, that's a fact. All living organisms are filled, from head to roots, with microscopic structures of astonishing complexity built around carbon. But couldn't we hope, among the 118 other stable elements found in the universe, to find some that are also capable of forming bonds whose breaking energy is accessible, while still being strong enough to persist in a stable state in their environment? To find these atomic gems, we must use elimination. By searching this table, the coolest in the universe as it lists every atomic element, the basic building blocks used to create main structures. To summarize broadly, here in this classification, the higher the elements are, the more abundant they are in the universe. Since we're seeking elements common in nature, we can eliminate the last 4 rows. In what we have left, we're looking for elements that are capable of forming bonds with other elements, and if possible, in large quantities. And for that, we need to find elements that are likely to share their electrons. I won't go into much detail and apologize to chemists for the shortcuts. I'm sure they're already objecting. Their neurons screamed with anger, as harsh as an anvil scraping a blackboard. But let's say that each atomic element has electron shells, regions within which electrons whirl around. And depending on whether these electron shells are filled to the brim or not, atoms are more or less willing to bond with others. In short, the ability of an element to form chemical bonds, to have a natural affinity with other similar atoms, will depend on how willing it is or not to share its electrons. So, in order to try to find a chemical element at least as effective as carbon for building complex molecules, let's start by eliminating all those who, being solitary, can't stand others, such as the noble gases helium, neon, argon, krypton, xenon, which have electron shells filled with electrons and are therefore extremely unwilling to give them up, just as they are to accept new ones. You may have noticed these elements, with almost no reactivity and a huge aversion to forming bonds, are all in the same column. In fact, in this table, all the elements in the same column generally behave in the same way. This will make things much simpler for us. Just to the left is the so-called halogen column, where you find, among others, fluorine, chlorine, bromine, and iodine. And it contains elements that have only one free spot on their electron shell. Therefore, it's rare for them to form more than one bond with other elements. If you add to this the fact that, in their pure state, they have an unfortunate tendency to react explosively with everything around them, while forming extremely strong bonds, it's clear that this isn't where we'll find what we're looking for. The elements in the next column, such as oxygen, sulfur, or selenium, can form two bonds. That's good, but it could be better. Elements like nitrogen and phosphorus in the next column can form up to three. That's significant, but we can aim higher. And here we are in the carbon column, with right below it the famous silicon, germanium, and tin, all of which have the ability to form up to 4 bonds. And that's where it starts to get really interesting. Especially since we're tempted to imagine that as we move further to the columns on the left, we'll have more and more possibilities for bonds, and so, an abundance of choices. Except that a serious downside is starting to appear, because in reality, the further we go to the left, the more these elements prefer to give up their electrons rather than share or gain new ones. That's why, in the universe, a large part of reactions involve atoms from the left side reacting with those from the right side. And everything beyond the column of carbon and silicon is actually not very willing to actively participate in the formation of complex molecular structures. That's for several reasons, often from being too reactive, like alkali metals such as lithium, sodium, and potassium, or forming ionic bonds that are way too unstable, or even metallic bonds that can only create repetitive crystalline structures. In short, you get it, we've ruled out most of them. After removing the heaviest elements from each column for bond strength, we're left with one block containing silicon and the fantastic 5. The Knops: carbon, nitrogen, oxygen, phosphorus, and sulfur. These 5 elements, combined with hydrogen, are unanimously found in all living things, and we've never found an organism that can do without any one of them. If you've been following this channel for a while, you know how much I love the Knops group. I've even dedicated several videos to them. Arranged together, these microscopic building blocks let us build the cathedral of life, a structure built entirely around carbon as its central element. The beams and keystones, you probably noticed that. The Fantastic 5 are accompanied by an outsider who also possesses great powers. An element located just below is capable of bonding with 4 other atoms at the same time, silicon. This is to really understand why we can project onto this element the idea of a form of life based on different fundamentals. Let's start by listing its strengths. Even on Earth it is, with carbon, the only element able to form complex and diverse molecular frameworks. Next, it benefits from quantity, because even though there are 10 times more carbon atoms in the cosmos than silicon on Earth, the latter make up more than 28% of the mass of our planet's crust, while barely 0.03% is made up of carbon. Okay, that's a good start, but before we get excited just because they're literally all around us, we'll also need to go over the long list of its broken promises by looking at its weaknesses. Silicon atoms, almost twice as large and heavy as carbon atoms, struggle to form double or triple bonds with themselves, unlike carbon, which does this easily. So, they usually form linear chains with single bonds. This becomes problematic when you consider that, among other things, double bonds are at the heart of geometry, in DNA's double helix. Add to that the fact that most of the complex molecules silicon is capable of building are unstable in water and break down easily at room temperature, and you start to have a little problem. And then, above all, its main weakness lies in the strength of its bonds, because unlike carbon, whose bonds tend to be of similar strength, this allows for a wide range of configurations. Different geometric by allowing molecules to easily change atomic partners. Silicon, once bonded, has a hard time letting go, which means it is much more limited in terms of versatility. To put it another way, for it, the grip of the first bond is always the strongest. This strength limits its flexibility, sometimes locking the compounds it forms into a rigid state. Let me explain. Among its range of possible partners, there is one that silicon is especially fond of, the one we all love to breathe. Put it in the presence of oxygen, and inevitably, those two will quickly bond and won't want to let go of each other. It may seem trivial, but on Earth, by bonding with oxygen, silicon eventually formed complex polymers known as silicates, which make up the majority of the rocks around you. Here, the main drawback of this almost unbreakable form of loyalty is actually the great stability of silicates. This greatly limits their possible chemical interactions. Also, because silicon almost always forms rocks when oxygen is present, there's another, even stranger consequence. On Earth, when animals breathe, they use oxygen to metabolize carbohydrates, basically sugars, and thus recover energy while releasing water and carbon dioxide. In this process, we extract energy from oxygen molecules and release carbon monoxide, too, which holds less energy. Now imagine hypothetical life forms on another planet. Extraterrestrial beings based on silicon are able to harness the energy contained in the oxygen present in their atmosphere by making it interact with long atomic chains from their own resources and, as a result, release not carbon monoxide, too, as all carbon-based life forms do on our planet, but silicon dioxide, silica, and carbon monoxide, too. We can see that some small practical problems are going to arise soon. Because yes, exhaling just under a kilogram of carbon dioxide per day for an average-sized person is not a problem. If you had to expel the same mass as sand through your lungs, you can see the problem. As a carbon-based life form, rocks, at first glance, pebbles don't really fit the idea we have of residues produced by living activity. Nor are they the kind of thing we'd like to see accumulate in our bodies. This hasn't escaped the notice of some science fiction writers who have had fun imagining them thriving on other planets. Alien crystal life forms that are completely devoid of lungs like animals, or stomata like plants. They breathe by extruding glass beads or small bricks through what serves them as a mouth. Okay, now we've completely gone off the rails with speculation. And here, it's important to remember that these lines of reasoning are completely biased by the fact that all of us here, without exception, are carbon-based life forms. Too fast. Trying to imagine these hypothetical silicon beings as crystalline creatures with a rocky appearance, inspired by what on our planet contains the most of this element. Consider that we, the carbon-based beings, are made of flesh and blood, of wood and sap, and thousands of other things. Materially, we have nothing in common with graphite, pencil leads, or diamonds, which are, however, almost exclusively made of carbon. So, by broadly exploring the types of known materials that incorporate silicon, it seems more logical. Put a lot of quotation marks. To imagine that these hypothetical extraterrestrials don't expel silica the same way oxygen entered, but perhaps have organs similar to kidneys that eliminate it. In terrestrial animals, urea would seep out while their exotic respiration would produce a viscous silicate gel. But again, the problem is these speculations stay close to what surrounds us. With creatures endowed with muscles, fluids, and skeletons made up of a whole range of materials that we've drawn from molecular forms, built from known silicon, prisoners of our carbon-based condition, stuck by the lack of alternatives to what we know, it's impossible for us here to imagine something radically different. Nevertheless, today, this lack of flexibility at the atomic scale of silicon suggests that if extraterrestrial life forms have developed on planets with conditions similar to ours, then they most likely must have been built around carbon. However, as biased toward this element as we may be, perhaps one way to imagine other possibilities would be to go back to the fundamental flaws of silicon. What's remarkable in this story is that, despite all these difficulties, none are definitive obstacles. Perhaps on celestial bodies with different conditions, there's even some hope. We know, for example, of solvents such as liquid hydrocarbons at very low temperatures, which are suspected to exist on the surface of the Moon Titan, which are, for complex silicon-based molecules, havens of stability. Silicones themselves are relatively stable in sulfuric acid, a substance that generally makes electron-rich species regret coming into contact with it. As for polysilanol, which is roughly the silicon-based equivalent of sugar, they are soluble in liquid nitrogen. In short, some weaknesses on Earth could very well turn out to be strengths elsewhere. And on worlds with radically different chemical compositions and temperature and pressure conditions, we can have fun imagining the existence of an extreme extraterrestrial biochemistry, a strange biochemistry with a different framework, and which, built around the properties of silicon, could have given rise to life in a playground very different from the one we know. Also, without needing to go that far into space, we already know of living beings on Earth that use large amounts of silicon, such as diatoms, small unicellular marine organisms capable of using the dissolved silica in seawater to build themselves magnificent glass skeletons. At the center of these structures live carbon-based beings encapsulated in a crystalline cocoon richly endowed with silicon. An element that, although it sometimes plays a role in certain biochemical processes by allowing some living beings to build themselves an armor, has never been found at the heart of the machinery. And even though there are in the Earth's crust some with 925 silicon atoms per carbon atom, Earth's undisputed king takes the stage. And yet, despite this undeniable domination, the question remains whether C is the only possible framework for life, or if could exceptionally come to write another grammar of life. On planets with different but not extreme conditions, all these questions might seem completely crazy to you. And yet, thinking about the exotic solutions that life could have found to thrive elsewhere helps us better define extraterrestrial signatures on other planets and understand the origin of life on the moon. Because, strangely, silicon could have influenced the life we know in its very nature. Examining carbon-based organisms at the molecular level, we find that all carbohydrates and their amino acids share the same orientation. For the same chemical composition, each molecule can have two mirror image versions. So, how can we explain that all around us and within us, we only find right-oriented carbohydrates and left-oriented amino acids, and not a little of both versions, or mostly their mirror form? One hypothesis for this oddity is that this direction of life was dictated to amino acids and carbohydrates by the primitive environment that saw them come into being. A silica-rich, rocky environment acted as a nursery for early complex molecules and spatially oriented carbon-based chemical reaction products on a microscopic scale.